Now let us study synchronous counters. Now to design a synchronous counter, one must know excitation table of the flip-flop which we are using. So before designing a synchronous counter, we will see the excitation table of T and JK flip-flop, because mostly we use T or JK flip-flop in case of a synchronous counter also. Now before explaining excitation table, let me differentiate synchronous counter and asynchronous counter. Now see, we have seen some asynchronous counters up till now. So in case of asynchronous counter, clock is not given simultaneously to all the flip-flops. It means that clock is given to the first flip-flop, and output of first flip-flop is used as a clock input to the next, okay, and output of next will be used as a clock input to the next, okay, like that. Means we don't clock all the flip-flops simultaneously. Means clock frequency of the clock input of flip-flops used will be different in case of asynchronous counter. In case of a synchronous counter, all flip-flops used will be given same clock input. Means clock frequency of all the flip-flops used in a synchronous counter will be the same. That is the main difference. Now let us see the excitation table of the T flip-flop. Remember, excitation table is derived from the truth table. So here, this is a truth table of a T flip-flop. Okay. So I am assuming here T flip-flop is a negative edge triggered. So when input is 0, it remains in a last state. When input is 1, it toggles. It toggles means if its output is 0, it becomes 1. If its output is 1, it becomes 0. So now let us see the excitation of T flip-flop. Remember, excitation table is derived from the truth table. Okay, now in excitation table, okay, see what is there. Present state, next state, and input required. Okay, present state 0, next state be 0. Now here present state is 0, next state also we want 0. So what input you have to give? Now see, in next state also we want 0, and present state also 0. Means input required will be 0. So if it is 0, it remains in last state, na? So this 0 will continue here. So input required will be 0. Present state 0, next state I want 1. Okay, present state 0 hai, next state I want 1. What input you have to give? What input you have to give at the T input? Here you have to give 1. Why you have to give 1? Because present state is 0 and we want 1 in the next state. Means we want toggling. Okay, so here in the truth table, see, when you want toggling, the input should be 1. So that's why here input required, T input required will be 1. Now present state 1 hai, and then next state I want 0. Okay, so here also we want toggling. That's why input required is a 1. Present state 1 hai, next state we want 1. So here from the truth table, see, if you want next state same, means input required is 0. Okay, so here 0. So this is called excitation table of a T flip-flop. And if you know the excitation table, then only you can design the synchronous counter, otherwise you cannot design. So now let's design mod 6 synchronous counter. So first thing, you have to find out the number of flip-flops required, as we have done in our synchronous counter. Same expression you have to use. Mod 6 is less than or equal to 2 raised to 3. So here 3 flip-flops are required. Why not 2 flip-flops required? Because 2 raised to 2 will not satisfy this equation. Okay, 2 raised to 1 will also not satisfy. Okay, so here 2 raised to 3 will satisfy. That's why here minimum 3 flip-flops are required for mod 6 synchronous counter also. Okay, then mod 6 counter will count from 0 to 5, and then again it will start from 0. So here present state and next state is written. Okay, so here 3 flip-flops are required, so that's why here Q3 Q2 Q1, Q3 Q2 Q1. Okay, 0 0 to 0 0 1. So what now, to go from this state to this state, what input is required, that you have to find out from the excitation table. Now here Q3, if you see, while going from this state to this state, Q3 remains same. Okay, Q3 remains same. Q3 remains same. That's why T3 will be 0. T2 also same. So that's why T2 will be also 0. But Q1, okay, has to grow from 0 to 1, means it has to toggle. So that's why input should be 1 from the excitation table we have written. The next state is from, it has to go from 1 to 2. Now while going from 1 to 2, what input is required? See, Q3 is same. Okay, so here T3 is same. If same, input is 0. Now here if you see, Q2 will toggle. Q2 will become 0 to 1. So here that's why T2 should be 1. And Q1 also has to toggle. It has to become from 1 to 0. So that's why this will be also 1. Similarly, next state, it will go from 2 to 3. So here, while going from 2 to 3, what input is required? See here this is Q0. Q0 has to grow from 0 to 1. So input required will be 1. Q2 has to go from 1 to 1, means it remains same, means this will be 0. This will be 0. And Q3 will be also same, so this will be also 0. Okay. Then next state will be 3 to 4. While going from 3 to 4, what input is required? See here, Q1 has to become 1 to 0, means toggling 1. This Q2 also has to become 1 to 0, means this is also toggling. And this Q3 will be again 0 to 1. This is also toggling. Okay. Then next state is, it has to go from 4 to 5th. So while going from 4 to 5th, Q1 has to go from 0 to 1, means Q1 T1 has to toggle 0 to 0. Flip-flop 2, that is Q2, has to go from 0 to 0 means it has to remain same as 0, and Q3 has to go from 1 to 1 means again same. Okay, then in next state it will go from 5 to 0. So here Q1 has to toggle, so that's why T1 will be 1. Q2 don't have to toggle, so that's why 0, and this Q3 has to toggle, that's why it has to be 1.